Why don't we get started for this session? So good afternoon. I'm Mark Davis from Intel. I'd like to tell you about a methodology and a set of tools that makes it much easier to create parallel programs from your serial program. I'm here representing the Parallel Advisor Tools Group, and I'd also like to thank Paul Peterson, who created many of these slides. So what's Intel Parallel Advisor? This is the tool that I want to tell you about today, obviously. It's a part of Intel Parallel Studio, which is a whole suite of tools for working with parallel programs. They're all part of plugins for Microsoft Visual Studio. Now, Advisor is not part of the current Parallel Studio, which I have some copies of here, which people may want to have to evaluate later today. But Advisor will be part of Parallel Studio. The next version, which comes out before, at the very beginning of Q4 of this year. So what are the important parts about Advisor as a quick overview? While you're adding parallelism to serial code, it guides you to make the good decisions at each step along the way. Secondly, many of the tools in Parallel Advisor use serial modeling of parallelism. So they only pretend that you have a parallel program, but your program really is still serial. And we'll see the benefits of that in a moment. And finally, Advisor is based on a time-tested methodology for adding parallelism. So it's a good starting place for learning about parallelism and how to add parallelism to your programs. So a quick digression on Intel Parallel Studio, since I brought it up. Again, the next version is coming out very soon. The first component, or what will be the first component, that's really the on-ramp to Parallel Studio, is Intel Parallel Advisor, which helps you find parallelism and helps you make your program parallel ready by correcting problems such as race conditions that you would have if you went immediately to parallelism. Intel Parallel Composer is a way of expressing your parallelism. It's the Intel compiler along with parallel extensions such as Cilk, Intel Cilk Plus, along with Intel threading building blocks, which we just heard about. Now, how many people knew about Cilk before Michael mentioned that? All right, so a few. Cilk is it's 3 keywords get you most of Cilk. So it's a very powerful and very simple language, and as Michael mentioned, it uses the scheduler is very smart, and TBB changed their scheduler to correspond to Cilk. So Cilk's something that you might want to look into in the future. The third component of Parallel Studio is Intel Parallel Inspector. That helps you find memory problems and race conditions in an already parallel program. So there's a distinction between Advisor, which is working on your serial program, and Inspector when your program is already parallel. And finally, there's Intel Parallel Amplifier, which lets you tune your parallel program. So much for the digression. We'll go on to Advisor. Now, the main part of, or one of the difficult parts about finding parallelism in your program is that you probably already have a parallel program lurking in your serial program. The problem is that your serial program may be over-constrained that causes problems converting to parallelism. For instance, you may have global variables that are being read and written by your algorithm, which makes it doesn't bother the serial program at all, but it may cause major problems for trying to parallelize and have different tasks dealing with those different variables. So over here on the right, we'll see this is the workflow pane that comes up in Visual Studio when you're running Advisor, and it shows you the 5 basic steps that you use in Advisor. The first one is to survey your target, which means to run a profiling tool. Survey is the profiling tool so you can find where you're spending your time in your program, and you focus on that when you want to parallelize. The second step is to annotate your sources, and we'll talk more about annotations, but that's a way of indicating to the Advisor tools where you want to have which regions you'd like to have parallel and which flavors of parallelism you want there. Next, having selected those places, you want to check that what you thought from your earlier profiling and where you chose parallel regions will still be giving you the kind of parallel speedup that you were hoping for. Next, you need to check correctness. And this is really a key point of looking for race conditions that would occur in your parallel program if it were made parallel in the places that you currently are specifying. Now again, these steps are still working on your serial program. Finally, you want to pick a parallel framework like TBB or Cilk or OpenMP or pthreads, and convert the annotations that you've put in into parallel constructs, and now you have a parallel program. And finally, after doing that, you can go on to use the other tools in Parallel Studio for expressing, finding further bugs, and tuning the parallel performance. So Advisor, Advisor is not an automatic parallelization tool. It's actually aimed to handle larger programs and larger sections of programs and messy programs. They're not aimed at nested loops the way that some auto-parallelizers are, where it's somewhat easier to do. Instead, it guides you through the set of decisions that you have to make and each step of the way of converting to parallelism. So the Advisor workflow I showed you just before can be augmented to the slightly bigger flow graph. These first 4 steps are the same as before. This new step, summary, the summary display shows a combination of your suitability and correctness results together in one place, so you can decide which parallel regions will give you the best return on investment. Because if you're working on large programs, it's going to take a bunch of effort, and you only want to focus on the places that will actually give you the best payoff and that don't have 1,000 race conditions that you need to fix. You also want to go on having found and fixed some of your bugs. You want to go on and go back and check both your correctness of your new program and whether it's still suitable after you potentially put in locking or reorganize the program some. So there's a little more to go on, more steps as it shows here. Sort of the intent of Advisor is to give you a lightweight mechanism for experimenting with parallelism in your program. So you can put in some annotation somewhere, see if you get the kind of speed up that you want and whether there's too much fix up that you need to do. And if it's too much, you can move things around, and you don't have to have your program be a correct parallel program just to see if it'll run. So that brings me on to the next point, which is sort of it's one of the key technologies that's used within Advisor, and that's serial modeling of the parallelism. So what that means is that, again, as I mentioned, the annotations specify where you want to have parallelism, and the tools model what that parallelism the behavior might be, but you're still running your serial program. So it's a huge advantage over having to change to parallel constructs first. So once you change to parallel constructs, you may have race conditions, your program may crash, it's not going to behave the way it did before. Under Advisor with serial modeling, your program still behaves exactly the way it did before. Your test programs should all run exactly the same way they did before. You don't have to worry about non-determinism of different threads or different tasks running at different speeds. It's still your same serial program. So this particularly allows you to refactor your program, modifying it to make it become more parallel ready while it's still having all its good serial characteristics. So are there any questions about the advantage of serial modeling? And we'll see what we do with it later on. Okay. Okay, I'll repeat the question. The question is, do you run it on the full program or on a cut down version? The survey step, which is the initial profiling, and the suitability step have very low overhead, less than 5%. So we encourage you to use large data sets and make sure that you cover your whole program. When we get to correctness modeling, the correctness modeling step is a very expensive step because there's lots of tracing, and we'll talk about that. So we encourage you to use a cut-down input data set. We still want you to cover all of your program, but instead of having a loop go 1,000,000 times to compute something 10 times may be quite enough to show what kind of data races you're going to have. So, because otherwise the overhead is pretty high.
My second question is, what the effect with some programs show different behaviors on different sizes of data sets. So some programs models could behave differently from large data sets. So at least be taken into consideration.
Do you mean performance characteristics?
Yeah.
Or no, those aren't taken into account. We aren't looking at some of the cache and memory coherency issues of small and large data sets. But since we aren't doing it automatically, you, the user of Advisor, can try those and see how those are impacted. And also later, once you have a parallel program, you can use parallel amplifier, which can give you a lot of detail about how the individual threads are behaving and whether you're getting affinity correctly, for instance, as one aspect of that. So good question. Thank you very much. So I'm on to Amdahl's law, which we heard about this morning. The key item, the key takeaway here is the amount of parallel speed up you get is limited by what you leave serial, the part that is still serial when you're done. And the example, if you parallelize 50% of your program and run it on 1,000,000 processors and the time is 0 for it, you still only get a 2x speed up. So the conclusion from this is that you really need to focus on the places where you have a large amount of compute time spent. So that hopefully motivate. Oh, did I? I'm sorry. I missed the programming model. That's obviously when you're doing real parallelism with fork join is the model that the Advisor uses. You have multiple threads all running at the tasks running at the same time, whereas with Advisor, we're actually running serially, and we run each pretend task independently, serially, and then we sort of pretend what would happen if they were all running at the same time. So we go on to the survey output, and so as I earlier said, you really need to have the profiling information although you may have a good idea of where good places are to parallelize, the profiling information gives you the quantitative information to make the best decisions about where you should do things. Now, if you were doing serial optimization, when you're doing serial optimization, forget about parallelism. When you're trying to optimize a serial program, you want to know the hotspots, exactly which parts of the program are consuming the most CPU time, that have the most self time. And here there's a column of self time, and that means it's just time spent in that function. And in order to speed up a serial program, you have to reduce the amount of time that's spent in that particular function, or there's no other way to speed it up. In contrast, when you're doing parallel optimization, you don't have to focus just on the hotspot. You can look at any place that has a total time, the large total time, where total time is time in this routine and all routines called recursively. The whole call tree starting at this routine. And the whole point there is that when you're doing parallelization, what you're attempting to do is distribute that compute time over as many tasks as possible. And that's how you reduce the elapsed time. Typically, when you parallelize something, you're not reducing the CPU time, you're actually increasing it because you have a lot more overhead and other things. But you reduce the time to solution because you're able to distribute the computes over a large number of tasks. So that's what the survey, what you're trying to do is look for call chains from the main program, from the main function to your hotspots, and anywhere along that chain might be a good place for a parallel region. And that's sort of what this shows you, a call chain in the survey display, and you see that there's a lot where the total time is 100% and then it goes down. Well, this will actually open up and show a lot more time in there. But it turns out that the solve loop turns out to be a good candidate. All of these are recursive calls, but solve is a good spot for parallelism, even though you see the self time is 0. If you're doing serial optimization, you would never have looked for solve because you're not spending any CPU time directly there, but it's the base of where the time is spent. On to annotations. As we mentioned earlier, you've decided from looking at the survey results on some places that you think are good regions for having parallelism, and so annotations are the way that you can pretend, or that advisor can pretend to have parallelism. The three key ones are parallel cite, which is similar to OMP parallel. It defines where your parallelism starts, and really more importantly, the barrier at the end where all tasks wait until they all get there before execution completes. Tasks, that's where you pretend, where advisor pretends to have execution running at the same time in parallel. And locks, lock regions pretend that only one task can execute at a time. So, and it turns out that annotations are actually just macros that expand into function calls to magically named, specially named dummy functions that when the advisor tools see them, it knows to pretend that particular parallel behavior. Okay. Advisor provides a wizard in the Visual Studio editor that allows you to easily add the right annotation. So you're shows being in Visual Studio Editor. You select a region of code, you right-click, and you'll get an annotation wizard. You can choose which kind of annotation you want. There's documentation about what it means. You can find out more information about it. But the important thing to realize and remember is that you are making the decisions about where the parallel regions are. Advisor's just helping you get the syntax right. And this is an example for with lock acquire or lock release. Okay, so we're on to the suitability that I mentioned earlier. Okay, we're doing okay on time. Now that you have your annotations for your parallel experiment, you want to determine if you're going to get the kind of speed up that you were hoping for when you chose those particular regions. And here's a fairly complicated output that we've attempted to help you with. The one thing to note first is we got more than a 5x speed up on 8 CPUs. So we did choose a pretty good site, at least the estimate is that this is a pretty good site. Now, as I mentioned, there's a lot of information here, but this suitability graph here is the thing to look at. It's a log-log graph. This is the speed up on the y-axis, and the x-axis is the number of CPUs. Now, if you're in the green, you're doing great, because you're getting almost linear speed up. When you're in the yellow, you're sort of so-so, and maybe you should make some alterations. If you're down in the red, that means you're actually getting a slowdown from the way that you chose your parallelism. And maybe that's not a good parallel site, or maybe there's some major change that you can make to make that better. Now, to help you with some of these, I've got a before. The top half is a before, and then below is an after. So in the before, you notice that the circles are down here in the red. So things are looking bad, except since the bars, the fact that it's not just a dot right down there, but that there's an actual bar, it means, oh, there's some leeway there. There's some options under which you can see a fairly good speed up. And if you look over on the right, here are some items that are parallel programming related, having to do with overheads of sites and tasks and lock contention, that are things that you might be able to make a difference about. So the important one to look at is reduce lock contention. Advisor is telling us that we can get almost a 4x speed up if we fix lock contention. And it also shows us that it recommends that we do this. So what does it mean to reduce the lock contention? Well, first of all, if you look in the after slide, it shows, oh, look, we're up in the green again. That's good, because we've checked the reduced lock contention. Now, what that means is that you, the programmer, have promised that you're going to fix lock contention. Advisor's not going to fix it. You're going to have to fix it, and you're going to have to fix it when you convert to real parallel, when you convert to your parallel program. Now, it turns out, well, you can make some changes in Advisor that when you carry them over, it will make it work better. For instance, in one of the homework solutions that you'll be working on, there's an opportunity to use a single lock to protect something. Now, it turns out if you do use a single lock, you may find that you'll get a lot of lock contention, and you might want to use some other solution there. I won't tell you what solution you might use, because that would be cheating. And unfortunately, Advisor works on Windows, and you guys, you all are using Linux. So if you could use Parallel Advisor, you'd be done with your homework in, I don't know, half an hour, and you'd have nothing to do with the rest of your lab time. So I had to keep it on Windows so that it wouldn't break the lab exercise here. Okay, so by now you're feeling pretty good. You found that your suitability shows you that you're going to get a really good speed up, but there's one caveat, or one major caveat, is that you haven't checked to see what your correctness results will be. Are there any race conditions? And if there are race conditions, can you fix them easily without losing all that performance that you were so happy about just a minute ago? So in this case, as we mentioned earlier, correctness modeling takes longer. It works better if you use a debugged version because of your program instead of an optimized version, because the debugged version does every single load and store, whereas the optimized version keeps things in registers, and the issues that you might have won't be seen by the tools. So let's go on and see what does correctness show us. There's a couple things to notice here. There are, I'll briefly describe what happens with correctness analysis. First, it runs your program keeping track of all your memory references and all the annotations so it knows where the tasks are. Then it models what kind of parallel behavior you could have, which task could run at the same time and stomp on the same objects at the same time, given the constraints of synchronization points, either from locks or from begin-end tasks. And then it shows you, it combines all the observations of errors into related observations are combined into single problems, which makes it easier to fix because you don't have you may have 1,000 instances of a race condition, but it's all because of one particular line in your program. So it combines them down into problems for you. So here, look over on the summary over here, and it shows that we have two errors and one remark, and the remark has to do with a parallel site. And now it turns out it's very important to have that remark about a parallel site because it tells you that you actually did execute your parallel site. You might accidentally have given the wrong input so that you don't even execute that parallel region, and you say, oh, this is great, I have no correctness problems, and it turns out you didn't actually execute your parallel region. So it's good to see a parallel site information. Now, the first error here that's highlighted is a memory reuse error. Memory reuse means that the numerous tasks use the same object, but in the serial execution, each task body initialized the variable before using it. Therefore, no values were intended to be passed from one task to another in the serial program. That's a good thing to know because really what you have is a case of incidental sharing, which you can fix by giving each task when you actually, you can make this modification now. Each task gets its own copy of that object, and then they won't be conflicting with one another. The second problem, the P2, data communication, that's an instance where values really are flowing from one of your tasks to another one in the serial program. That's usually more difficult to fix. We saw in examples earlier today, we've seen places where you use reductions or you have to use locking to make sure that things are correct. The other thing, since memory reuse is highlighted here, down below are source snippets of different instances of observation. So here's a write and another write and a read. And those all could happen as race conditions. Now if you double click on a certain one of those problems, you'll get another source view which has more information. For instance, it has the stack information over here. You can click on any one of these stack elements to see the corresponding source code. That way you can track how you got to the place that was giving you problems. What else do I want to say? Also, on either of these, anytime you have the source code, you can double-click and go directly to the editor so you can make whatever changes you want to make when you figured out what's wrong. Okay, and having done that, you want, as I indicated earlier, you may want to repeat that loop around correctness back to suitability and correctness again, to both either make sure that you're doing the right thing. Again, you can use successive refinement to go through this loop. You're either getting closer and closer to a parallel ready program, or you finally decided this particular parallel region, I really wanted it to work, but it's just not working out. I should spend my time focusing on another parallel region. In either case, the idea is to be able to either decide this is good and I'm done with it, or this is bad and I'm done with it and I can go on. The idea is to be able to get your parallelization more easily and more quickly by giving you the right tools for doing so. So earlier I mentioned the summary view. What it has is it shows you your performance here and the amount of correctness problems. Now this is the NQueens program, and there's only, as earlier we saw, there's only two. We're only looking at one parallel region. There's only 2 errors. You have one very good speed up. And we know how it turns out we can fix the errors. But if you had a large program with 10 or 20 parallel regions that you were trying to work on, this would allow you to see which regions have the best payoff and aren't too hard to fix. I should focus my time there, fixing those, and I'll see what kind of parallel speedup I get. Now this is also the time, once you've decided on what parallel regions you want to use, this is also the time that you need to decide what parallel framework you're going to use. So you're going to use TBB or Cilk or OpenMP or POSIX threads. And having done so, you need to convert each annotation into the corresponding parallel construct. Now that's another reason that survey is convenient, is that the survey display shows all of the annotations in your program. So you can take any annotation here, double click on it, you're immediately in the editor where you need to make the modifications to get to your parallel framework. So in order to help you get to a parallel framework, we don't have an automated way of doing it, but we do have documentation on how to convert our annotations to TBB and to Cilk. Intel Cilk Plus. Intel registered trademark, registered Cilk TM Plus. Sorry. I have to say that for marketing, not to do unpleasant things to me. I have to say it officially. So this shows a case of a counted loop, and as Michael showed us, you can use a parallel for. This is a very simple parallel for. I'm not using a blocked range. I'm just using a plain old integer. I'm using lambda expression as well. So you can see how tiny this translation is. I mean, this is kind of clunky. This, excuse me, it looks like OpenMP for Fortran, where you have the opens and closes. And we in the advisor team apologize, but that's the best we could do with macros. If you have a sequence, of tasks, here's 2 tasks. For TBB, you would use the parallel invoke, and again, you could use lambda expressions to make it very simple. And if you don't have lambda expressions, you have to use functors, and Michael was showing the details of what functors look like. And those of you, I'm like Michael. I'm from C, and I've sort of gotten into C++, but I don't live and breathe templates and functors. But maybe many of you are much more familiar with that and feel much more comfortable with that. So let me do a quick recap of how Parallel Advisor works. Since we've seen the pieces, now we'll see them all together quickly. So you've got your serial program in C or C++. I probably forgot to say this only applies to C and C++ and currently only on Windows. So you use the survey tool to do the profiling and find out where your time's spent. You add your annotations for your parallel regions, and you still have a serial program. It still works just the way it always did. You now use the suitability tool to figure out the performance characteristics, and the correctness tool to find out what kind of race conditions and memory problems you may have. And now you fix the problems, and you go around this loop. You repeat a couple times as you fix the problems and look at what your suitability results are. But again, you're still working on your serial program. All right, you're still working on your serial program. Finally, it's time to convert to real parallel constructs of your choice and to move on to the other components of Parallel Studio now that you have a real parallel program, which is what particularly Inspector and Amplifier work on. So in conclusion, I hope I've been able to show you how Advisor can help you find parallel programs as you convert them from your serial program. Excuse me, we're switching mics. How is this? Can you hear this fine? Okay. So, as I said, I hope I've been able to convince you, or at least have the benefit of the doubt that Advisor may be able to help you convert your serial program into parallel. The modeling information provides you information about your parallel experiments. The methodology takes you through all the decision points that you're going to have to make, and it attempts to provide you with all the information, or most of the information you're going to need to make those decisions as you make your transformations. And it allows you to progressively refine your program to become more parallel ready while still being serial. And again, I hope I've been able to show you the advantage of staying serial as long as possible in order to get your program right. So now that I've told you about it, a question?
Yeah, I was curious. A couple of slides ago, you were showing these annotate those statements, which is the final product. Yeah.
Oh, these, yes.
So this is the final product of this stage, basically. So is this code? Is this something which could be compiled with the C or C++?
I should have. The question is, I think if I can I compile this with a regular compiler? And the answer is there's an include file that defines these macros, and you compile it with any compiler that you want to. And since they're calls to dummy functions that just return, all they do is slow your program down a tiny bit by having a function call. So your program, that's why your program, even with annotations, works just the way it always did. It makes no impact or minuscule impact. So thank you for asking that question. It clarifies that. But it brings another question. Yes?
Yes. Maybe 3 or
pages before this one, there was a conclusion that no parallelization exists. And as you tried a bunch of things, none of them worked, and therefore you conclude that the code can't be parallelized. But is that a correct conclusion? I mean, would a more accurate conclusion be merely that the path you've chosen didn't lead to parallelization, that perhaps an altogether different approach would have allowed you to parallelize?
So the question is, I may have misspoken in saying that there is no, you've determined that there's, in the path that you followed, there is no parallelism, or all the choices you have taken have been rejected because either they don't have performance or there's too many correctness issues. And the question is, but maybe you could have chosen a different place. And absolutely, you may need to choose, particularly if you're looking at the call chain, and you're looking down close to main. So you're pretty far, sort of typically, the closer you are to main, the more program you're covering. So the goodness from a suitability standpoint is if you find a loop really far out, that'll be great because you're going to cover almost all of the execution time. So that's a goodness. The bad part is, since you're covering the entire program, you have much more opportunities for having parts of that program referencing global variables or having dependencies among them. So you really have to, you may pick an outer loop and you run into horrible things. For instance, the homework assignment, from a suitability standpoint, the obvious place to parallelize is the time step. It's doing a time step from 1 to 1,000 or something. And at each time step, it sees, it moves all the particles a little bit. You say, this is a great place to parallelize. I could do 1,000 things at once. Except, if you do correctness modeling, you'll now see, oh my gosh, every single thread, all of these tasks are manipulating the same set of particles. And it obviously, parallelizing at that level isn't going to work because each time step, there's a definite dependence between each time step wants what you did in the previous step. So you're going to have to go farther up, farther down the call chain toward the leaves to find some place to parallelize. But that's sort of somewhat answering the question of it's not a science, and it's not a, oh yeah, absolutely, it's going to be this place. You're going to have to go back and forth, picking and choosing. The goodness is what kind of speed up you're going to have, and the badness is how many correctness errors am I going to get, and thinking more closely, here are the dependencies. Oh, this really is a time step 1 is the input to time step 2 is the input to time step 3, and if I can't parallelize there, it's really lockstep. So I'm glad you asked that question. I may have answered several other questions along the way, but it was very, very valuable. Let's see if I can go back to, okay, I was going to say, so if you're interested in Parallel Advisor, how do you get a hold of it? Or, well, the first thing is that Parallel Studio is a website here that I've mentioned, and that will point you at the current version of Parallel Studio, which they said is going to be updated by early Q4, and as part of that update, Parallel Advisor will be added to it. So if you want to have a copy of Parallel Advisor before then, you can send me email, as I've indicated down at the bottom, and I can get you an evaluation copy. The other thing is I have a few copies of the current Parallel Studio, which again does not have Advisor in it, but these will, when the new version of Parallel Studio comes out, these will be automatically updated to the new version of Parallel Studio, and it will have Advisor. Now, if people are interested in trying this and providing me with some evaluation information, I can hand these out to people, so you can come up afterwards, and I'll ask for your name and an email just so I have a record of that. The current version of Parallel Studio supports Microsoft Visual Studio 2005, 2008, and the new versions that will be coming out will also support Visual Studio 2010. And one very nice thing of Microsoft Visual Studio 2010 is it supports lambda expressions, so that if you are like I am and prefer writing a tiny little lambda expression instead of doing a big functor, with Visual Studio 2010, both the Intel compiler, all the Intel compilers, and Microsoft Visual Studio will support that, and you won't have to write the functors. Question?
Are these tools targeting the native C++ code combined with C and Visual Studio, or the code that targets Microsoft.NET framework? In Visual Studio you can do C++ running on top Microsoft.NET framework, or you can run it natively. So
This is for native C and C++. It's not for managed code, or not all of the tools currently work on managed code. So, the question was whether the tools work for managed C++ or native C++. So we are on to questions. So are there other questions? So thank you, and good luck with your homework example. There's lots of, well, I should say with a homework example, it will show you that with a homework example, there's, I don't know how many people have looked ahead. I sort of looked ahead, and there's the simple serial program, which is n squared, and you can parallelize that. An advisor can help you parallelize that, but you'll still have an n squared program that's running a little faster parallelized. Advisor is not going to say, wait a minute, it's n squared and you could do it a better way. It's not solving the algorithmic, what's the key way to speed up the algorithm. It will take whatever serial program you want and help you make it parallel, but you really have to figure out first that you have, a good expression of the serial algorithm, or an efficient expression of the serial algorithm before you do that. So I'm sorry. So thank you. And